So now that we have a basic understanding of some reactions catalyzed by enzymes and their requirement for cofactors or prosthetic groups, we're going to use this week to look more specifically at enzyme kinetics as well as the regulation of enzymatic reactions. So enzymes in general help reduce the amount of transition state energy required for a reaction to move forward. And they do this primarily through the following mechanisms. The first is by stabilizing the substrate within the active site. We've also seen from the previous week that this also increases the substrate concentration in a local area. The active site is adept at excluding water from the area, as well as stabilizing the transition state of the reactants. And we've also seen how enzymes use cofactors or coenzymes to help with the transfer of an intermediary group. So the kinetics of an enzyme-catalyzed reaction are summarized here, and it's mainly determined by the properties of the catalyst or the enzyme. Like all catalysts, the enzyme creates a new reaction when it's added. So if we look here, in a spontaneous reaction, you start with an initial substrate, which is spontaneously will generate a product. When you add our catalyst or our enzyme, we generate this new intermediate or this enzyme substrate complex that facilitates binding of the substrate, again within an active site, to assist in catalysis to generate this enzyme product. The rate of this reaction is readily described by the Michaelis-Menton equation, which relates the initial velocity to the concentration of the substrate and two parameters, which we'll talk about, which are Km and Vmax. So the Vmax is defined as the maximal velocity of any given reaction. And this can be achieved at an infinite substrate concentration, while the Km of a reaction, as shown here, is defined as the substrate concentration needed to achieve 1/2 Vmax. The Michaelis-Menton constant Km characterizes the affinity of the enzyme for the substrate. A high affinity of the enzyme for a substrate therefore leads to a low Km value, and vice versa. The full Michaelis-Menton equation is shown here. We're not going to use this for calculations in the course, but it's important to conceptually understand the relationship between Vmax and Km. In this graphical rearrangement, it's difficult to determine exact numerical values for both Km and Vmax. However, to alleviate this issue, the Michaelis-Menton equation can be rearranged in such a way that the measured points lie on a straight line. Using the reorganized Michaelis-Menton equation, we can plot these values on a Lineweaver-Burke plot. In this plot, the y-axis represents 1 over velocity and the x-axis is 1 over substrate. This allows the intersections of the line of best fit with the axes to produce value for 1 over Vmax here and -1 over Km here. We'll use Lineweaver-Burke plots to identify the impact of the addition of a competitive or non-competitive compound on enzyme regulation. However, before addressing the regulation of enzymes, it's important to note that the Michaelis-Menton equation can only be used to describe enzymes that display simple saturation kinetics. This is best illustrated here if we go back to our comparison of myoglobin and hemoglobin. Remember, myoglobin has this simple saturation curve which we could use and describe with the Michaelis-Menton equation. However, for hemoglobin, which has cooperative binding properties, we have this sigmoidal curve. And in order to describe the kinetics of the sigmoidal curve, you would need to use the Hill equation, which is represented here. The regulation of Michaelis-Menton type enzymes falls into two major categories: competitive and non-competitive. Competitive inhibitors will bind the enzyme at the active site. Many of these competitive inhibitors function as substrate analogs. Under these conditions, in the presence of a competitive inhibitor, a higher substrate concentration is required to achieve a half maximal rate. The Michaelis-Menton constant, Km, therefore increases. However, when substrate concentrations are elevated, this will ultimately displace the inhibitor and you will achieve optimal Vmax. So in the case of the addition of a competitive inhibitor, there's no change in Vmax, however there's an increase in the apparent Km. In contrast, non-competitive inhibitors bind the enzyme on a site that's alternative to the substrate binding site, and therefore its effects cannot be overcome by increasing substrate. The addition of these compounds will therefore decrease the overall Vmax of the enzyme with no change in apparent Km of the substrate. The action of these inhibitors can be illustrated clearly on Lineweaver-Burke plots. The actions of both competitive and non-competitive inhibitors on our Michaelis-Menton constants Km and Vmax can be best illustrated here. If our green line illustrates enzyme kinetics with no inhibitor, you can see that 1 over Vmax is represented here by an intersection with the y-axis, and negative 1 over Km is represented here by our intersection with the x-axis. If we remember, the addition of a competitive inhibitor will change the Km with having no impact on the Vmax. This becomes very apparent. The addition of a competitive inhibitor we see does not change the intersection with the y-intercept, again consistent with no change in Vmax, but it does change the Km by increasing the apparent Km of the enzyme. And that's shown here by a shift in our intersection of our kinetic line with the x-axis. If we compare Lineweaver-Burke plots of an enzyme reaction with no inhibitor or the addition of a non-competitive inhibitor, we can see the relationships clearly here. With the addition of a non-competitive inhibitor, remember there's no change in Km, and that's shown here by no change in intercept of the x-axis. However, there's a decrease in Vmax with the addition of a non-competitive inhibitor, and that's shown here with a shift in the 1 over Vmax with the addition of the non-competitive inhibitor. So let's finish with a question to use our information of enzyme kinetics. If a mutation is made within the active site of an enzyme resulting in an increase in Km, which of the following will be true with respect to the enzyme kinetics? A. The enzyme will require a lower substrate concentration to reach 1/2 Vmax. B. The enzyme will require a higher substrate concentration to reach 1/2 Vmax. C. The concentration of the substrate needed to reach 1/2 Vmax will not change. Or D. The Vmax of the reaction will increase. Let's break this question down a little bit. First of all, an increase in Km results in a decrease in substrate affinity within the enzyme. If we also remember that Km is defined as the substrate concentration required to meet 1/2 Vmax, we know that an increase in Km will result in an increase in substrate concentration required to reach 1/2 Vmax. This makes B the best answer to this question. In this case, the enzyme will require a higher substrate concentration to reach 1/2 Vmax, which would be consistent with an increase in Km.